Good morning again. This is Dr. Jingbo Louise Liu. So today we are going to finish the types of intermolecular forces. This part of lecture is more focusing on the bonding forces and the non-bonding forces. I listed them in a table for comparison to recall about the nature of intermolecular forces. As we mentioned, you have two types of forces. One is called repulsion, another one called attraction. The attraction forces, you have bonding forces and you have non-bonding forces. Those non-bonding forces are called intermolecular forces. Normally, people also call them van der Waals intermolecular forces. Van der Waals intermolecular forces. What are the natures of these intermolecular forces? Number one, the intermolecular forces arise from the attraction between molecules with partial charges or between ions and molecules. Again, the intermolecular forces is the attraction between what? Between molecules. It's not within molecules, between different molecules, because you have partial charges such as your H2O. Oxygen is negatively partially charged. Hydrogen is positively partially charged. Also, you may have sodium chloride, sodium positive ion, chloride negative ion. Second point, the intermolecular forces are relatively weak compared with the bonding forces. The reason is the intermolecular forces involve smaller charges that are far apart from each other. So if you still remember the bond strength, bond length, so let's recall for your covalent compounds and your van der Waals radius. If you have your covalent compounds, you have two nuclei. These two nuclei are going to share electron pairs. The distance between the two nuclei, you consider them the bond lengths. This is one molecule. Between two molecules, such as, assume this is our chlorine, Cl2. So chlorine and chlorine, you have the nucleus. Those nucleus are between two different molecules. So you have this is one molecule, diatomic, another molecule, diatomic. The distance between these two nucleus, that distance you call it van der Waals distance. This van der Waals distance is the distance between your non-bonded atoms in adjacent molecules. These two molecules, they are the neighboring to each other. Those two molecules has no bonds. So these two atoms, you form a bond by sharing electrons. And also, we have another point. So imagine this nuclei. The distance to this shared electron, the outer layer of your shared electrons, this distance you call the covalent radius. Between the molecules, this nuclei to the sphere of your atom, that distance you call the van der Waals radius. The two nuclei, that distance, the two nuclei which are not bonded, that distance you call the van der Waals distance. Your van der Waals radius is approximately half of the van der Waals distance. So closest distance between the nuclei of two non-bonded atoms. So the van der Waals radius normally is larger than your covalent radius. If you compare this covalent radius and your van der Waals radius, this value, this covalent radius usually is smaller. The further away the atoms, the weaker the interaction, the attraction it is. The table listed the comparison of your bonding and non-bonding forces. This first part showed you 3 bonding forces: ionic, covalent, and metallic bonding. So I also showed the models. You have positive, negative, negative, positive, interacting, interoccurring. The basis for this ionic bonding is caused from cation and anion attraction. This energy usually is high, 400 to 4,000 kilojoules per mole. For example, your sodium chloride, any ionic compounds. The second bonding forces, covalent bonding forces, refers to 2 nuclei share this bonded electrons. They call the shared pair. The basis of the attraction due to the nuclei attracted to your paired electrons or shared electron pairs. So you have 1 shared electron pair. This energy is reasonably strong. It's 150 to 1100 kilojoules per mole. For example, your hydrogen gas, your oxygen gas, your nitrogen gas. The third bonding forces we call metallic bonding. This metallic bonding, if you still remember, is resulted from the nuclei and the core electrons, which is surrounded by those electron seeds. You see positive, 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 they represent the nuclei and the internal or inner electrons. And this yellow or orange colored dead spheres represent the delocalized electrons. The basis of the attraction is resulted from your cation and delocalized electrons. Those delocalized electrons also form the electron sea. And these delocalized electrons glue your metals together. This energy is 75 to 1,000 kilojoules per mole, such as commonly used metal, Fe, your iron, your steel, copper, your gold, silver, etc. This second part of the table listed the non-bonding forces, also called intermolecular forces, also called van der Waals attraction. Non-bonding forces can be distinguished into ion dipole, hydrogen bond, dipole, ion-induced dipole, dipole-induced dipole, and London dispersion. The models are listed. If you have a positively charged ion, if you have a polar molecule, this positively charged ion and its negatively partially end will be attracting to each other. The basis of the attraction is resulting from the ion charge. This ion charge to your dipole charge. This energy is much weaker. It's 40 to 600 kilojoules per mole. However, this ion dipole intermolecular forces is considered the strongest intermolecular forces. It's still about 1/10 to 1/100 of your bonding forces. For example, if you dissolve your table salt, sodium chloride, into your water, you are going to see the ion dipole intermolecular forces. The second one is called hydrogen bond. Hydrogen bond is not a bond, it's intermolecular forces. You also have a positively charged end of your hydrogen, negatively charged end of your non-hydrogen. In this case, this lone pair and your positively partially charged hydrogen, they are attracting to each other. The reason is polar bond to hydrogen dipole charge, your polar bond to your hydrogen dipole charge. In this hydrogen bond case, you must have another molecule such as this A, either nitrogen or oxygen or fluorine. You must have either nitrogen, oxygen, or fluorine. It can be both. Hydrogen must be directly bonded to this one of the nitrogen, oxygen, or fluorine atoms. Those nitrogen, oxygen, fluorine that have very strong electronegativity. Hydrogen bond ranges from 10 to 40 kilojoules per mole, such as 2 molecules of your water molecule. They can form hydrogen bonds. In between, you use the dashed line. Did you see this dashed line? Dashed line represents the intermolecular forces. The third one is called dipole intermolecular forces. If you have two polar molecule, polar molecule refers to the molecules have the uneven distribution of your electron pairs, of your electrons. Your electron density is not evenly distributed. So this resulted into dipole charge to dipole charge attraction, negative end to positive end attraction, ranging from 5 to 25 kilojoules per mole, such as if you have these two molecules, they are dipolar molecule, both polar molecule. Your chlorine is more partially negatively charged, the iodine more partially positively charged. They attracted to each other. Another forces, intermolecular forces is called ion-infused dipole. Imagine you have such as Fe ions. You have oxygen molecule. Your oxygen is supposed to be nonpolar. However, due to the induction of the positive charge, one end can be instantaneously negatively charged, another end instantaneously positively charged. Therefore, your ion charge and the polarizable electron cloud attracted to each other. This instantaneous polarization you call polarizable electron cloud. So this attraction ranges from 3 to 15 kilojoules per mole, such as your Fe2+, such as in your red blood, your heme attracted to your oxygen. And also you have dipole-induced dipole. Imagine you have a polar molecule, you have a non-polar molecule. This non-polar molecule can also be polarized. Therefore, your dipole charge to the polarizable electron cloud attraction, so glue the two molecules together. This energy, this attraction ranges from 2 to 10 kilojoules per mole, such as if you have hydrogen chloride and your chlorine. Chlorine Cl2 is a nonpolar molecule but can be polarizable. This dipole charge to polarizable electron cloud is the reason for this intermolecular forces. The very last one called London dispersion. This London dispersion applicable for the two nonpolar molecules. However, your electron can be distributed unevenly, instantaneously. Therefore, you have polarizable electron cloud to polarizable electron cloud attraction. This attraction is fairly weak, but depends on the different molecule, ranging from 0.05 to 40 kilojoules per mole, such as you have two fluorine molecules. So they are going to subject to the London dispersion. So I also showed the different types of intermolecular forces. So if you have your polar molecules, this polar molecule, they are going to result into dipole attraction. Positively partially charged, negatively partially charged, they are going to attract to each other. So positive pole and your negative pole, positive pole, this is positive, this is negative pole, they are attracted to each other. In the solid state, they are very well aligned. In the liquid state, they are a little bit random. And then also your dipole moment is going to affect on your boiling point. What's the reason? Dipole moment is the measurement of your polar molecule, the polarity of your molecule. Usually, the dipole moment increase, for the similar molecules, your boiling point will be, yes, thank you, increased. So I showed several molecules for you to understand. Now about your hydrogen bond, particularly we want to mention it. Hydrogen bond, hydrogen bond is possible for molecules which have hydrogen atoms. These hydrogen atoms covalently bonded to a small, highly electronegative atom. such as oxygen, nitrogen, or fluorine. So you also have electron lone pair, such as in your water, oxygen has lone pairs. And then the intermolecular forces, hydrogen bond, is the attraction between your hydrogen atom and the atom from another molecule, such as fluorine. Your fluorine from another molecule and the hydrogen from the second molecule. That attraction, particularly the hydrogen positively partially end and these lone pairs, this attraction forms hydrogen bond. Similarly, in your water, your oxygen has lone pair. In your NH3, for example, hydrogen is partially positively charged. These two forms intermolecular forces. Also be careful, your intermolecular forces, you are going to use dashed line, dotted line to represent it. The bonding forces, you use a solid line to represent it. Your hydrogen bonding is going to affect on your boiling point very significantly. Because of the existence of hydrogen bond, the boiling point for the related molecule dramatically increased. For example, you have your charcoal gas, OSSETE. Those 4 different molecules that form the hydrides. So these compounds, usually you measured by the molar mass. Generally speaking, the larger the molar mass is, the higher the boiling point or melting point is. In this case, your water has smaller molecule, but the boiling point is very high. At room temperature, it's a liquid. The other ones, they are gas. Yes, the hydrogen sulfide is gas. This hydrogen H2TE may not be gas. So in this case, your boiling point is not in this low temperature, in high temperature. The reason is hydrogen bond. And also your hydrogen fluoride compared with hydrogen chloride, compared to hydrogen bromide iodide. So HF, you form hydrogen bond. Therefore, boiling point significantly increased compared with other 3 hydrogen compounds. Similarly for your nitrogen, NH3, PH3, ASH3, and SBH3, those hydrides. Your NH3 forms hydrogen bond. Boiling point very high. On the other hand, your methane, CH4, SH4, GEH4, SNH4, these 4 molecules, there's no hydrogen bond formation occurs. Therefore, your boiling point just follow by the molar mass. The increase the molar mass resulted in the increase of your boiling point. And also, we have several examples. I want everybody to show the existence of hydrogen bond. I have 3 molecules. First one, C2H4, called ethane. Second one, methanol. Third one, called CH3CO and H2. So what's your plan? Number 1, you are going to identify whether those molecules contains oxygen, nitrogen, and fluorine. Nitrogen, oxygen, fluorine is very critical. The first molecule, you don't have a nitrogen, oxygen, or fluorine. Therefore, 99% first molecule does not exhibit hydrogen bond. And if you have oxygen and nitrogen and oxygen, you also need to figure out whether the nitrogen or oxygen or nitrogen covalently bonded to hydrogen. If they are covalently bonded to the hydrogen, you may consider intermolecular forces in this way. So this is one molecule with the electron lone pairs. There's another molecule that atom bonded with hydrogen directly through covalent bond. So let's take a look. Our solution, number 1, again, C2H6. You didn't see any nitrogen, oxygen, or fluorine. Therefore, hydrogen bond is not going to be formed. Second one, methanol. Methanol, you do have oxygen, and this oxygen directly bonded with your hydrogen. This is CH3. These 3 hydrogens, they directly covalently bonded to carbon. They are not going to be involved in hydrogen bond. So how you are going to write it down, the hydrogen bond? So you have your methanol, the first part, this is my methanol. My oxygen has 2 lone pairs. Second methanol, Ch12A. This hydrogen from the second molecule is going to be forming hydrogen bond with oxygen from another methane. And also the last one, this is CH3CONH2. You have a carbon-oxygen double bond, you have nitrogen-hydrogen, so bonded to each other. So you can have 2 possibilities. First one, this oxygen double bonded with your carbon, you have 2 lone pairs. Your nitrogen bonded, covalently bonded with your hydrogen. These 2, hydrogen and oxygen, form a intermolecular forces hydrogen bond. And also you can form 2 hydrogen bonds between 2 molecules. Your oxygen and the hydrogen forms bonding. Your nitrogen and the oxygen, nitrogen and oxygen, they form another one. If you can form 2 hydrogen bonds, this molecule you form a dimer. This is even stronger, even more preferable. And then for your molecules, if they are polar molecule, they are going to induce another non-polar molecule, so resulted in distortion. So therefore, we need to know polarizability and the induced dipole. A nearby electrical field can induce a distortion in the electron cloud of an atom, or induce the distortion of the electron cloud of your ions, or this electrical field can induce a distortion of the electron cloud of your molecule. For a non-polar molecule, this induces usually is temporary dipole moment. So your polarizability is temporary, instantaneous. For a polar molecule, the electrical field enhances the existing dipole moment, so resulting in further polarizability. The polarizability of a particle is the ease with which its electron cloud is distorted. Your electron cloud distortion occurs. You want to make this a current eased. And then the trend of your polarizability. Normally, smaller particles are less polarizable. Larger particles are easily polarizable. The reason is the electron can be held more tightly within your smaller particles. Smaller particles hold your electrons tightly. Polarizability increases in the same group from top to bottom. Polarizability increases down a group. The reason is the atomic size is going to be increased from top to bottom. Therefore, the electron density cloud, that cloud going to be easily distorted. Polarizability decreases in the same period from the left to the right. Polarizability decreases across a period because of the increasing in effective attraction of your nuclei. Cations are normally smaller than the parent atoms. Therefore, your cations are less polarizable. Your negatively charged anions, they are usually bigger than the parent atoms. The anion shows higher polarizability. So this is essentially about the different polarizability. So we also showed you dispersions among the different molecules. If you have a spherical particle, you have a polar molecule. These two, they can attract it to each other. If you have 2 polar molecules, so positive and negative poles, they are going to attract it to each other. So they are going to be eventually aligned with each other. Again, positive, negative, negative, positive, attracting to each other. In most of the cases, the molecule distribution is more random, but this attraction, intermolecular forces attraction occurs throughout your samples. The London dispersion. We want to emphasize the London dispersion because this attraction arises when the instantaneous dipole occurs. You have a particle. Those particles, they are not a polar molecule, but they induces a dipole in another, resulting in attraction between each other, such as if you have oxygen O2 and oxygen O2, they are going to induce the molecule to become a polar molecule instantaneously. Therefore, they are attracting to each other through positive, negative, and attraction. Dipole forces exist between all particles, increasing the energy attraction in the matters. And the London dispersion forces are stronger for the more polarizable particles. If you have your particles, they are easily to be polarized, that attraction will be stronger. In general, the larger particles experience stronger dispersion forces than the smaller one, because the larger molecule, they can be more readily polarizable. And then we also have some examples. I have a couple groups of compounds. I want everybody to do the comparison, which one has higher boiling point. I have group A, B, C, and D. What's our plan? Step 1, we are going to examine the formulas and the structures for the key differences between the different molecules. You may ask yourself, are the compounds ions composed of ions? Are they ionic or not? Are ions present, such as your magnesium chloride? You do have ions. Are those molecules polar or non-polar, such as B group B? This you have two molecules. Are they polar or non-polar? And then if they have a nitrogen, oxygen, or fluorine bonded to hydrogen, is there any hydrogen bond can be formed, such as your group C? You have oxygen, hydrogen, they bonded to each other. Yes. If your molecules like group C, they have the same molar mass, but they have different shapes. What are you going to consider? You are going to consider the symmetry. The symmetry. Our plan, our solution, sorry. So bonding forces are normally stronger than the non-bonding forces. Bonding forces are about 10 to 100 times stronger than your non-bonding forces. Hydrogen bond is a strong intermolecular forces. Hydrogen bond is a type of dipole-dipole, but it's strong. London dispersion forces are decisive when the difference in molar mass or molecular shape. If you have molecules that are non-polar, and the molar mass are very important, and the molecular shape are also important if they have the same molar mass. So let's see our example A. You have magnesium chloride, you have ions. Therefore, you are going to find the ionic bonding. So your phosphorus trifluoride, PCl3, consists of the covalent bond, but they have two different types of molecule. Therefore, you are going to have a polar molecule. So in this case, you have your dipole-dipole intermolecular forces. Dipole-dipole intermolecular forces much weaker than ionic bonding. Therefore, magnesium chloride has higher boiling point than the phosphorus trifluoride. You have another two molecules in your sample B. So both molecules, they are covalent compounds. They both composed of polar molecules, and they have something special. So this CH3 and H2 and your CH3F, if you calculate the molar mass, they are the same. Therefore, you are going to determine which one is going to form hydrogen bond. The first one. So you have nitrogen bonded to hydrogen directly. The second one, CH3F, this hydrogen bonded to carbon directly. So therefore, the first molecule, they are going to form hydrogen bonds between hydrogen and nitrogen due to the existence of your electron lone pair and positively partially charged hydrogen end. Therefore, you form a hydrogen bond. In other words, the first molecule, CH3 and H2, this amine-based compound has a very high boiling point compared with the compound which is a fluoromethane. Example 3. You have methanol and ethanol. Both molecules are polar molecules. Both molecules have oxygen which directly bonded to hydrogen, meaning both molecules, they are going to form hydrogen bond. In this case, you are going to compare molar mass. Methanol, the first one, ethanol, the second one. The second one, ethanol, has a larger molecular molar mass. Therefore, the dispersion will be taken into consideration. So your ethanol has a higher boiling point than your methanol. Ethanol, I believe, is 78 Celsius. Methanol is 46 Celsius. The last group, you have hexane. Hexane is 1 to 6 carbons. They form a straight line structure. This molecule is a non-polar, it's not polar. Another one called 2,2-dimethylbutane. You have 4 carbons in the straight line. You have one branch, another branch. In this case, you have 2 molecules have the same molar mass. Both molecules are not a polar molecule. What you are going to consider? You are going to consider the molecular shape. One is cylindrical. The first one, hexane, is cylindrical. Another one is 2,2-dimethyl. You have 2 branches. This branched molecule has a lower symmetry. Therefore, hexane has a higher boiling point than the 2,2-dimethylbutane. And double check. So I listed the different boiling point for the groups of compounds. So what we figured out, our prediction is correct. I think about this methanol, I believe it's 46 Celsius. Somebody maybe double check on me. So fact checked. So also remember, the London dispersion forces are existing in technically all the compounds.